Number 62. In this case, we have a wall. We have a bar going out. We have a wire coming up here, a cable they call it. And we have a sign hanging here. Hanging from this. We have that this distance here is 80 centimeters. That the bar is 200 centimeters long. And that the distance from here to here is 250 centimeters. We're also given that this pole is 5 kilograms. And that the cable, the tension in the cable, is equal to 300 or maximum of 300 newtons. We want to figure out the mass of the sign. Another static equilibrium problem. So what we're going to do is, this is the bar here, the bar that's connected, and this is at an angle theta here. We're going to draw a free body diagram of that bar and all the forces that are acting on it. So we have tension going off here at an angle theta right there. Okay? We have that the center of mass of this, we have the mass of the bar times gravity. That's happening exactly at the center of mass. And then we have to put this the mass of the sign here. Now we could do this in two parts. We could split it in half and put half here and half here, or we could realize that this comes at one point here, so we could just transfer to that to one point up there because it's going to be equally separated between those two. That's usually the easiest way. Now we got to realize this is 80 to there. This is 1.2 across here. The center of that's 0.6, so the distance to that from this side here to the mass of the sign times g, that's 1.4 meters. This is 1 meter to here, and the whole thing across is 2 meters all the way across. Now there's also a vertical force and a horizontal force acting on the bar at this end being held up by the wall. But we're going to do this as net torque, and we're going to make this our rotation point over here. Because we don't know the horizontal and vertical force, that way they don't have any torque to worry about. Then I look at this and I say, oh, T, the tension pulling upward, is going to make it go in a counterclockwise, so that's positive. T times the distance, which in this case is 2, times the sine of the angle in between, which is theta degrees. Then we're going to do the sine minus the mass of the sign times gravity times its distance, which we already figured out is 1.4, times the sine of the angle, but in this case this angle is 90 degrees. And then the last one is minus the mass of the bar itself times 1 times the sine of 90, which is also going to be 1. This is going to be 1. And this is all going to be equal to 0. So if I rewrite this, this becomes 0 is equal to 2t sine theta minus msg times 1.4 minus mbg times 1, which I'm not even going to write. And we want to solve this for the mass of the sign. So we're going to mass of the sign. So I'm going to move that to this side. So this becomes 1.4 msg is equal to 2t sine of theta minus mbg. And then ms is just going to be equal to 2t sine of theta minus mbg all over 1.4 g. Now a couple things we have to do before we can plug in all the numbers is we have to figure out what theta is. But theta, we know these two differences, is just the inverse tangent of opposite 250 over 200. That gives me what the angle is. And the angle theta is equal to 51 degrees. And then I plug that in and I plug on all the numbers. This is 2 times 300 times the sine of 51 degrees minus the mass of the board, which they give us is 5 times 9.8 over 1.4 times 9.8, and we get that the mass of the sign is 30.4 kilograms maximum. That is your answer.